this afternoon's session, so we probably want to start on time and get rolling. But I want to welcome everybody back to the ESIG workshop and the session 3, where we're going to be talking about grid forming requirements and specifications. So as we think about the future power grid, and one of the things that we've been talking about is the addition of renewable resources, and then you peel back renewables and you find variable renewable resources, and then you peel that back a little bit further and you find, oops, all of these things have inverters inside of them. And then you peel that back again and you find, wait, there's all sorts of different kind of inverters. You have grid following inverters and grid forming inverters, but we're going to focus on grid forming inverter technology during this particular session. Really dive into it a little bit, because we see this as kind of the technology that's going to take us into the future and allow for really high levels of inverter-based resources to be interconnected to the grids. One of the big things along those lines really is developing specifications and requirements. And we have a lot of great speakers here that are going to talk about their experiences from around the world and give us an idea. There we go. We got our last in-house speaker. If I talk long enough, they'll all show up. Okay, so we're going to go ahead and get started with this. Our first speaker from the ESIG group is Julie Matevosyan. Okay, so I'm going to turn it over to Julia, and I'll while she's getting prepped up, I'll read a little bit of her background. Hang on a second. So Julia is the chief engineer at ESIG, has more than 20 years of experience in the power industry. Prior to joining ESIG, she was also the lead planning engineer at the Electric Reliability Council of Texas, or ERCOT. While she was there, she worked on adequacy of system inertia response, system flexibility controls, and performance issues related to high penetration levels of inverter-based generation, and how to put those into an ancillary service market design. So with that, I'm going to turn it over to you, Julia, and get us started on this particular topic.
All right. Thank you, Ben. Thanks for introductions. Good afternoon, everyone, and thanks for coming to our workshop. All right, so I'll start with a little bit of background about how this work came to be. So in March 2022, we released a report about the role of grid forming inverters in systems integration. And so the idea was to provide some background on what grid forming resources are, how they differ from grid following, what projects already exist today deployed in the world, what testing you need to do, what specifications are out there. And then we followed up with grid forming a workshop in June in Denver that was 2 days fully dedicated to just grid forming technology and various aspects of how they impact the grid. And in that workshop, in the second session, if I remember correctly, Andrew Isaacs from Electranix, who've done a lot of good work with HECO, he said, well, Hawaii is already faced with this really high shares of inverter-based resources today, and they have acute need for inverter-based resources, and namely grid forming batteries to provide grid stability and ensure reliability of the system. Well, the rest of the US, where there is still plenty of synchronous machines on the grid, and they are still providing reliability services, we have this unique window of opportunity to procure, test, and gain experience with this relatively new technology without little risk to blacking out the system. And so we shouldn't wait until we are in the same situation as Hawaii to start gaining experience. We should try gaining experience now. And then that was followed with great research from our Berkeley lab that put out this nice charts looking at the interconnection queue and how interconnection queue grew over time. And Charlie showed that chart yesterday as well. And so if you see, they look at the interconnection queue, there is around 500 gigawatts of storage sitting in that interconnection queue, either standalone or co-located with solar. And in the absence of any incentives, all of this storage will be built with existing and traditional grid following technology. And then we had we had a webinar on what National Grid in Great Britain is doing. We had it in August, and they are already taking some proactive steps in deploying grid forming technology on their system and testing it out and producing requirements. And so I got contacted by a professor in Texas who asked me, well, how does it apply in Texas? Because I live there and I worked for ERCOT for a while. And so I put a paper together just thinking about how Texas grid could benefit from it. And I always thought, well, it's not only related to Texas grid, it applies to other grids as well. And that's how this decision maker brief, the way we called it, came out, and it just recently been released. So I'll use bits and pieces from both the ERCOT paper as an example, but also this more general paper that we just put out. So look, if you focus on ERCOT system for a bit, ERCOT has more than 35 gigawatts of wind already installed, 15 gigawatts of solar, and 3 gigawatts of battery, which is 1 to 2 hours duration already on the ground. The peak load is 80 gigawatts. The penetration peak was 69% in April last year. So most of this wind and solar, and also big portion of these batteries is going into West Texas. So that upper left portion of the map, because of good resource availability and also good land availability. And so, but that part of the grid is also relatively weak. There is little load there and little to no synchronous generation in that area. So what it resulted in is a number of stability constraints, what ERCOT calls generic transmission constraints. And these are constraints on one or a number of transmission lines to try to address stability issues. So basically ERCOT is controlling the flows on these lines and doesn't load it to full thermal capacity to avoid some of the stability issues that may happen. And if you see in this middle chart in there that the number of this stability constraint grew over time. You probably cannot see numbers, but you can see there's going up. And on the right-hand side, you can see a chart that's showing how curtailments of wind and solar increased over time. So in blue bars, you see installed capacity of solar or of wind, from 2014 to 2020. And then yellow is solar. And then these two lines, the lower line is wind curtailment and the upper line is solar curtailment. So most of it is because of the stability constraints, some of it because of overproduction during shoulder seasons at nighttime. So to address the stability constraints and to increase transmission over those transmission lines, what can be done is you either can put additional supporting equipment into place, such as synchronous condensers, and ERCOT put 2 of those in 2016 to make the grid in that area stronger and increase transfer limits from that area. But currently ERCOT also is looking and putting extra 6 synchronous condensers in the West Texas to deal with this large constraint that is top one constraint currently. One other thing that can be done is you can put additional transmission lines, and these transmission lines effectively just reduce the electric distance from this weak grid area to stronger sources. So it's not for thermal transmission to increase the thermal capability of transmission lines, but it's just to reduce the impedance between the weak grid area and the strong grid area. And this is very expensive solutions, and to show that it has economic benefit, it takes a lot of time and a lot of inverter-based resources in the area that are being curtailed. And so they're not easily implemented. That's what I wanted to say. So as we said, there is this advanced controls that are currently being, some of it is already commercially available, some of it is still being developed. And these controls can be designed to provide within equipment limits most of the capabilities that synchronous generators are inherently providing today. They can have stabilizing effect in areas with low system strengths, and they can improve stability of traditional inverter-based resources with grid following controls. And if these controls are implemented on inverter-based resources that are currently in the pipeline, they may provide more cost-effective solution than installing them with existing traditional grid following technology. And then you need extra supplemental equipment such as synchronous condensers or extra transmission lines to solve those stability issues that they bring about. And just to illustrate what I'm talking about with this example, imagine this is West Texas or Texas Panhandle, and you have grid following inverter-based resources in this area. And then external grid is far away connected with transmission lines, long transmission lines. And so you already have some stability constraints in this area and limit export from this area to avoid hitting those stability issues. So now if you are planning to build a new inverter-based resource, a new battery in this area, and it's going to be grid following, now you're running into more stability issues potentially, and you need some additional supplemental equipment, say a synchronous condenser, to improve stability in this area. But if on the other hand, this new battery is built as grid forming, then possibly you don't need this extra piece of equipment, the synchronous condenser in the area. So that's when I'm saying it's more cost effective. I'm not comparing, similar size battery, grid forming battery with similar size synchronous condenser in costs. I'm comparing extra costs of having grid forming battery versus having grid following battery and synchronous condenser. So that's where it comes like more efficient. So grid forming controls can potentially be implemented in any type of inverter-based resource, also wind and solar. But to provide some of this grid forming behavior, there needs to be an energy buffer. And then that means that wind and solar resources would need to operate below what's maximally available from the resource. So they need to pre-curtail to have energy buffer all the time. And in addition to apply grid forming control in wind turbines, it may result in greater mechanical stress on some of the mechanical parts in wind turbines. It is solvable, and there are some prototypes and some research available there, but it's just probably results in extra cost. And the battery is already an energy buffer because it's a battery, so it's only software changes that are needed in the battery to make it grid forming. So you may ask, okay, if it's just software changes, why don't we deploy these batteries in the queue today as grid following and then retroactively change them into grid forming at a later stage when we actually need it? And it may be possible, but also retrofitting can potentially result in additional cost. Changing control strategy is large material modification, and so that will probably require restudies with the utility that the battery is interconnecting at. You need to make model updates, so it may cause additional delays and costs. And there's a number of batteries with this advanced controls, grid forming controls already been deployed around the world, and further deployment is happening at the unprecedented speed right now. So if you look at existing and new batteries behind constraints in ERCOT, you can see that on the left-hand side, you see what's already been installed. And on the right-hand side, you can see planned batteries. In darker color, it means bigger batteries being planned in these areas. And on the right-hand side, you see in blue already installed capacity of batteries. So in 2023, right now, it's 3 gigawatt. There is additional 4 gigawatt with signed interconnection agreements and financial security posted. And there is additional 600 in 2023, and then potentially 3 gigawatt in 2025 that are with signed interconnection agreements already, but they haven't yet posted financial commitments. So these projects are relatively likely to come. Maybe it takes slightly longer time, but they will eventually get built. And in the absence of any requirements or incentives for grid forming controls, all of these batteries will be built as grid following, and they will go in the areas that are already behind transmission constraints. So potentially they're just increasing need for additional supporting equipment, such as synchronous condensers, for example. And you may say, well, this is untested technology. We don't have requirements. We're not sure how to formulate these requirements. But I wanted to bring up this example. I think Mahesh, I don't see him in the room, but yeah, Mahesh brought up this example about a year ago in this very room, maybe even. And he said, well, we already done this before. We've tested capabilities of grid following inverters to provide some of the services that were only provided by synchronous generators at the time. And there was a number of pilot projects that First Solar and NREL has done in the US, where they tested grid following inverters' capability to provide primary frequency response, fast frequency response, voltage support. And if you look at where we are today, many of the services are being provided by inverter-based resources that are installed in the US. So as a proof of concept that we've seen those tests, and then system operators went ahead and started either requiring this or allowing inverter-based resources participate in ancillary services markets. So similar pilots can be ran on inverter-based resources that are currently being built. It's more advantageous if a pilot is run on a number of inverter-based resources in the same area and from different manufacturers, so that we can test not only capability of each single plant to provide services, but also the interoperability and across different manufacturers. And in parallel with this pilot would be advantages if system operators could carry out studies using manufacturer-specific models and test overall benefit of, say, if all batteries that are currently in the queue are grid forming, what are the benefits and how much of this we need? Do all of them need to be grid forming? How to incentivize it, how to specify it? So just I wanted to conclude with call for actions. Deploying advanced control capabilities on batteries is a low-hanging fruit, and it's a good solution for weak grid issues today. And weak grid issues will be increasing problem if we continue installing grid following inverters in the same areas that are far away from the rest of the synchronous generation. But this opportunity may pass soon because we have this large interconnection queues. And if we install all of these inverters with traditional capabilities, then retrofitting may not be an option open to us anymore. Without any specifications and incentives, these batteries will be built as grid following. But if specifications or incentives are out there, then new batteries can be installed with grid forming capabilities and save us some cost on transmission assets such as synchronous condensers or new transmission lines. So ISOs, RTOs, utilities can work with stakeholders and carry out these benefit studies and figure out if deploying grid forming technology on their grid has benefits. And we can learn from areas such as Hawaii, Australia, and Great Britain, and use it as a guide as we are developing our own requirements. I just wanted to bring up a couple of things, a couple of ongoing initiatives that are related to this and could be of interest. NERC Inverter-Based Resource Performance Subcommittee is currently working on a white paper, trying to answer the same question, but more practically. So if I am utility today, if I am system operator today, and I would like to test this technology, I would like to deploy it, what do I do? And so it talks about high-level interconnection functional specifications for grid forming batteries potentially, how to get good quality models, and how to test and verify grid forming capability with what we know today. And then it has a number of examples with several manufacturer-specific models that are tested and ran through those tests that the document suggests. And then we have 3 ongoing project teams within ESIG under high share of IBR task force within a reliability working group that are related. And I'll start with one from the bottom. This is on advanced inverter control testing. So basically, if we look at all these high-level requirements that exist today, how we can test inverters today to show that they have grid forming capability, and that we also mean physical tests and we mean simulation tests. And we are going to leverage some of the NREL's practical experience and try to disseminate it further with our membership and in the industry. We're also doing another project on new services with high share of inverter-based resources. So this one is looking at when we get very few synchronous generators and they are not providing the services anymore inherently, what does the system need and how do we define it, how do we quantify it, and what of these inverters can provide. And then the last one is on stability assessment methods with high shares of IBRs. And this one is looking into producing a practical guide for oscillation analysis. And with that, thank you very much. And
Okay, so our next speaker is actually virtually coming from Germany, I believe. So our next speaker is Mario Ndreko. He is with TenneT. He has basically been working with TenneT on the topic of grid connection code and compliance with offshore wind power plants, HVDC transmission, basically working on looking at the specifications for grid forming inverter technologies as they relate at the bulk system level. And so, Mario, can you hear me?
Good afternoon. Can you hear me?
Yes, we can hear you. So I'm going to go ahead. I'm going to run
Good
your
afternoon.
I'm going to run your
Yes,
slides.
yes,
You tell me when, and I will change
yes.
them. And
Thank you.
okay,
Thank you.
so
Good afternoon also to everyone there. Sorry, I cannot see you. Good afternoon from Germany. We are at around 11 o'clock at night here. So first of all, many thanks to Mr. Charlie Smith for inviting me and for this exchange. And as it's a pleasure to exchange, of course, and it's a pleasure to bring the work that we are doing as ENTSO-E. And I will explain a little bit what ENTSO-E is, what we are doing, and how this is all related to the discussion of grid forming. You see there a big disclaimer, which I had to put because the work and that we are doing is progressing, in progress, and the material that I will share today reflect the input that ENTSO-E has provided to the European regulators and our association for the development of future connection codes. So this is actual until last November that I will discuss today, and of course work is in progress. I will explain later. So next slide, please. First of all, what is ENTSO-E? So ENTSO-E is the European Association of the European Transmission System Operators. So in principle, it's let's say an association which includes all TSOs, transmission system operators of Europe, which work together and cooperate in grid planning, system operation, research and innovation topics. You can see approximately we have ENTSO-E 39 members representing 35 countries in Europe. And as said, we are working together. We are cooperating on cross-border issues and on topics which are more European level, and of course, which has a big impact on the system. And one of these topics is, of course, the system planning and the development of future system needs and the design of the future grid. And when we say future grid, we mean, or at least in what we in Europe foresee, it's a target grid of fully decarbonized network running as much as possible, and if possible, close to 100% of renewables. So among the big pillars of designing the system is what we call development of the connection network codes. So connection network codes is in principle the European legislation, which every member state, every country in Europe, every state in Europe has to translate and to make it at national level, let's say national law. And these connection codes define a set of requirements which are obligatory or not obligatory, exhaustive or not exhaustive for the connection of grid users like generators, demand and HVDC system. So the connection codes, of course, are mandated usually by the European Union and with its, let's say, energy with ACER, which is a European Union agency for the cooperation of the regulators in Europe, and they are drafted and they are updated. They are revised in a sequence of 5 to 10 years by law, as the system is changing, and of course the system needs are different, the grid will be different, etc. So we have been working, next slide please. We have been working in the past 2 years, next slide, slide 3, yes, as ENTSO-E together with our European experts on connection codes on how to, at least in the last 2.5 years, how to update the current versions of the connection network codes, especially the network or RFG, the requirements of generators, And this has been done always, as you can see on the left part, with scope of bringing new system needs. So the system is changing. We see that it's getting dramatically changed in terms of inertia, in terms of system strength in some areas. And of course, it's not only the system needs and the system is changing, but also the experience we have from the first round of the network board requirements for generators. We got a lot of experience from the national implementation. Of course, there were things which could be changed. And of course, a lot of feedback which we get from our stakeholders, because at the end of the day, these are grid users, the project developers, the manufacturers, which have to comply with the set of the connection code requirements. And also, of course, there are also their feedback, which we welcome, and we work all together in the content of the Grid Connection European Stakeholder Committee to update the new version of the requirements for generators, for example. So this led to kind of a list of amendments that ENTSO-E developed in the past years, like, and of course, this as you see, must-have amendments, important changes we have to do, and of course, nice to have and low priority amendments. So this is in process, how it work, and the European Union, of course, has, next slide, please. The European Union has mandated the agency of the European regulators, each member state, to update the connection network code. So we had an official process which is going on. That's why I said that the material presented here today, at least for the grid forming part, which I will show, reflects only the position, only the proposal of our association of ENTSO-E. It's not, of course, something finalized. So as you can see, there's a whole process starting from Q1, Q2 2022 and ending up end of 2023. And this process involved, of course, it's led by ACER, by the European Union Agency for Cooperation of the Regulators, and it's supported by stakeholders like ENTSO-E, the Association of the wind turbine manufacturers, solar manufacturers, and all grid users. So we are at the moment halfway on that, and what I will present you today, and I think that's why I was invited potentially, is to give the view of grid forming capability. So how ENTSO-E has proposed that grid forming capability would be or should be part of the new version of RFG. Next slide, please. So after explaining or let's say putting a little bit the boundary conditions of the work, so what network codes is, how this is amended, I would like to go a little bit now to the way that we proposed, at least to the regulators, for the changes, and of course for including grid forming capability as in the network code RFG. So what we all clearly see is that this is something related to power park modules. This is related to generation units that are converter based, for sure. And what we have today in the grid is, of course, a list of capabilities like these generation units shall mandatorily comply with in order to get connection, in order to get connected and to generate. And this reflect, let's say, the two boxes up: frequency ranges, voltage ranges, fault through capability, things that, of course, they are standard today and everybody does. But what we see as a need is clearly that all the European TSOs see a need that in the new version of the requirements for generators, let's say RFG 2.0, yeah, we see clearly a need to have grid forming as a mandatory requirement for all new PPMs. And when we say mandatory, I will explain in the later stage what it means, but also only within the power ratings, the current ratings, and the energy offer of the PPM. So we have seen it as an important need, especially with an horizon of 2030, 2040. So, and this is important also to take into account that the whole process of amendments takes years. So if, let's say, end of this year will be a final draft submitted to the European Union for vote, there will be 1 year for voting. And there is a horizon that the new RFG, let's say, legislation will go into force into something like 5 years from now. So we are talking that on horizon 2027, 2028. Next slide. So how we specify this? How we put grid forming capability into the European level, let's say, for the connection of the PPM. So as some of you may know, in Europe we categorize the generators in 4 types. There's a type A, B, C, D, and of course these are categorized based on their significance. So determination of significance based on their size, capacity, and voltage. So as you can see, we have type A, B, C, and D, and this is, let's say, a table. And you can see up for the continental European synchronous area, the threshold of the upper, let's say, capacity of every power generating module. That is, and what does it mean in terms of megawatt? So the idea is that we put the capability for all these types, some of them non-mandatory, some of them mandatory. So mandatory means that the member state has to apply this because it is kind of a European law. Non-mandatory is that the member state may apply it depending on their system needs. Next slide. So going a little bit how we have proposed this to be done. We start, let's say, from the type A power park module, which is the small one, and it's kind of until 1 megawatt on a European level. Some countries have this threshold a little bit lower. So we have proposed to define, and it's also important to take into account that the RFG as the legislation takes the requirements cascaded. So if a requirement is type A, let's say, it goes to type B, to type C, and type D. So for the type A, let's say we have specified, let's say, the core requirement of the grid forming, and we did it in 3, let's say, articles or clauses, saying that within the power park module current limits, energy and power ratings of the power plant module, the performance should be a voltage source behind an impedance during normal operating conditions and course immediately after grid disturbance. This is, of course, non-exhaustive as a requirement, but we have the mechanisms when this is applied to guide the national implementation of this to every member state with what we call the implementation guidance documents. Next slide, please. So as I said, the capability is defined during normal operation within the power park module current limits, within the power park module voltage limits and energy buffer. And also it's defined during the first instance following grid disturbance. So in our understanding, grid forming means also the inherent response of the converter unit, the grid interface converter, during the first instance following grid disturbance. For example, if there is a voltage drop and a voltage phase angle jump, until from the operating point of the PPM of the converter until it reaches its current limit, the current should flow naturally. That's like a synchronous machine. That is defined in this clause, let's say, during the first instance following grid disturbance, and it defines in part 1 and 2 exactly how they should be done. And the third part, which is the C, next slide, please. It defines during the disturbance period. So during the disturbance period is the part which the converter has reached its current saturation, its current limit, and then it is allowed, of course, to make actions like reducing the internal voltage in order to keep the current within the acceptable values of the converter. So these clauses, let's say, of this article A, B, and C define, in our understanding, on a European level, and this is what we have proposed to our regulators, and we are discussing at the moment also with our stakeholders on how to define on a European level and a high level, with a non-exhaustive way, grid forming capability. So in principle, if you read in detail this, we understand this not explicitly as the capability of a power park module to have additional storage or to have, let's say, energy buffer, but rather within the converter ratings to behave as a voltage source as long as it has not reached the current limit. So we have seen this has benefits for the system. This ensures, let's say, that we will not face controlled robustness problems in weak connection points. And this is what we have called it, let's say, as a mandatory requirement. And this will come, let's say, usually for the big and the medium-sized PPMs. So a mandatory requirement means it's kind of a minimum technical requirement that every new, because the RFG 2.0 will apply only to the new units or power plants which are connected. It means in principle that within the current ratings and the power range of the converter, we would like to have the voltage source behavior. If, of course, some TSOs would like to, let's say, use grid forming for provision of synthetic inertia, for example, or to enhance, let's say, the rock-off, then of course this could be done, but this means additional cost in investment of storage behind it, and this means, of course, that could be part of a potential future market. So in short, as we have proposed as ENTSO-E, is to specify in the European level voltage source behind an impedance as a mandatory requirement, at least for medium and big size PPMs. Of course, next slide. This is non-exhaustive, as said. That's why in the relevant regulation there is a clause, Article Y, let's say E, which says that the required dynamic performance of the power pack modules for the paragraphs which I presented above and its associated performance parameters shall be specified by the relevant TSO. So it's very important also from our side that when this applies, that we have a good set of ranges, a good set of parameters, exhaustive values that each member state would put in its national regulation, and of course will test for compliance. Because at the end of the day, it's not only the requirement that should be there, but it should be also followed by a solid and, let's say, sound way of how you verify compliance, what type of disturbances should be tested, how should be tested in the lab or with the simulations. So this is something that at the moment we are working on, and we would like to work together with our stakeholders, which mean the project developers, the wind turbine, solar manufacturers, in the coming 2 years to have a solid dynamic performance, let's say, of grid forming PPMs, which would be kind of standard for Europe, and each member state would have to select a specific range of these values that would fit better the system needs, because you can imagine Spain sitting at the edges of the Iberian Peninsula have different system needs than France, which is in the center of the continent. So that is in short. If you go, I think time is going a little bit late. If you go to the next slide, please. I just wanted to say that the basic requirement is there, and of course, for big units, next slide, sorry. For big units like Type C, as we call, which is, or Type D units, we don't stay only to this part of the mandatory requirements. We also specify we require to have detailed integration studies or control interaction studies, as we do already today with other PPMs. So the relevant system operator may specify that the study is required to cover potential adverse control interaction. So, and of course, we have also additional requirements for the sake, if there are big PPMs, transmission connected PPMs, that they may also survive, or they should survive islanding. So in Europe, we have also the big challenge that although it's not very often, the system splits may occur. We have in 2021 two, of course, with small impact at the moment, but we don't know in a future system what the impact would be, especially if the imbalance is big. So in that sense, for the big power park modules of a certain capacity, let's say, we require also the capability that they stay as much as possible connected during the islanding, which means in principle that they have to withstand big angle jumps and high rock off. So that is a short my presentation. And as said, this you can of course visit the link. I put a link in the beginning to the disclaimer, and there is from the website of the European regulators or agency of the regulators, and you can find the proposals of ENTSO-E. We have also a big set of RFG amendments, so approximately 63 amendment proposals tackling not only grid forming, but for example, fault through capability of small generating units like type A, as we called, high voltage through capability, force oscillations. We have a lot of storage proposals. So we see, as Julia said in the previous, storage an important part of the future system. That's why we also see that storage should follow primarily the same requirements as power park modules. And there we have also submitted also as ENTSO-E our view and proposal for inclusion of storage to the RFG. And of course, another big topic before I close is rock-off immunity. So we see, as said, the system split as an issue, and that's why we have proposed to increase the rock-off withstand capability to values of 4 hertz per second for 250 milliseconds duration, for example, just to cover this. But of course, this is under discussion at the moment, under negotiation with the stakeholders, and we see how this will progress. So that's short from my side. Thank you very much for listening, and I'm happy to take a couple of questions if there are.
From Electranix Corporation, Lukas is a system study engineer who's experienced in performing state-of-the-art electromagnetic transient modeling and simulation of large systems with high levels of renewables. Going to give us some interesting insights into the world of grid forming inverters and where we're headed. So I'll turn it over to Lukas. Thank you.
Excellent. Thank you. Yeah, thank you to ESIG, Charlie and Ben for having me on this panel. It's an honor to be here. Yeah, I'm a study engineer with Electranix Corporation. We do primarily EMT modeling and study work. Today, I'm going to be discussing the Electranix perspective on grid forming, specification, and testing. So we've had, most of our grid forming experience has come through extensive work in the Hawaiian system, involvement in NERC IRPS groups, as well as a range of other grid forming projects in the US and Australia. So thank you to those entities for allowing us to work with you. But that being said, the views and opinions expressed here are those of Electranix. Okay, so talked about this many times already, but why are we talking about grid forming? What's driving the need? It's that incidence generation is pushing above 75%, up to 90% and beyond in several small and medium-sized grids. And the trend, the trend is to go further closer to 100%. And that's driving the need for grid forming, because without grid forming, we do see instabilities in some of these systems. For example, in Hawaii, we have some relatively near-term planning cases that are showing instability without grid forming inverter equipment. So grid forming requirements are needed to confirm grid forming capability. And that means that at a minimum, we're looking to confirm, similar to what was just presented, a near constant internal voltage phasor in the subtransient and transient timeframe, synchronism with other devices, and we need them to regulate active and reactive power appropriately to support the grid. That kind of is the working definition that came out of a grid forming white paper by NERC back in December 2021. There's a lot of other requirements and capabilities that have been proposed by UNIFI, Great Britain, HECO. Just now we heard from TenneT. So there's a lot of guidance out there for grid forming specification already, but there's not really much out there for how to actually test for these requirements. So a large part of defining grid forming specifications is coming up with a functional definition for what we mean by grid forming. So there's a few ways that this can be done. One way would be to specify the kind of theoretical behavior of the control topology that you're kind of looking for. So if you hear reference to virtual synchronous machine or Drupe-based control, from our perspective, that's not really recommended because it's kind of being pretty prescriptive about what's going into that black box that the OEM is providing you. So, in order to allow for some, new technologies to come along, maybe that's not the best approach. Another method is to define grid forming by an expected dynamic response out of, looking at PQ response resulting from changes in the system, voltage magnitude, frequency, phase angle. So you could take your grid forming inverter, hook it up to an infinite bus and apply those step changes on that infinite bus. And if you have an idea of what kind of responses that would elicit from a grid forming inverter, you could classify it according to how it responds to those types of changes in the grid. Another method would be to look at the kind of frequency domain response of the inverter. So you could perturb the inverter at various frequencies, and depending on what you see in the frequency domain, you could lump it into one category or another. For example, if you're looking at impedance only, like if we're saying that grid forming inverters are kind of like a voltage source, essentially, then you would expect that to have a lower impedance than the kind of corresponding grid following inverter. So that's obviously a research topic, and a lot of more work would need to go into that in order to actually be able to utilize that method, but I think it could be done. And then the last method, which is kind of going to be the focus of my discussion today, is going to be to observe the performance of the device in response to some well-defined tests that you would only expect grid forming inverters to be capable of surviving or operating in a stable manner. So primarily that's going to be the test where we take it from a grid connected mode and then we disconnect the grid and kind of see whether it can kind of survive that type of islanding situation. And I'll talk more about that slides to come. And just another note that the type of functional specification is going to be in large part dependent on how many categories of grid forming you're assuming. If you have, if you're assuming a battery project and you just want to decide whether it's grid following or grid forming, and you're not splitting out different categories of grid forming, then it might be pretty straightforward to kind of draw that line. Whereas if you have various types of grid forming that you're specifying, like grid forming with or without inertia, grid forming with or without primary frequency response, then you're going to get a more complicated definition and a more complicated set of tests that you would need to define grid forming. So I'll talk a little bit about the HECO approach to grid forming specification. So as some of you know, new battery projects in HECO are required to be grid forming. Non-battery projects are not prohibited from being grid forming, but none have shown up yet. So this has been out here for a number of years already, and HECO's had a fair bit of experience testing specifically the models for grid forming capability. So in that system, initially all plans, grid following or grid forming, are tested for a suite of things like initialization, voltage, frequency, fault ride through. And then there's an additional set of extra grid forming only pass fail type tests that are required to confirm grid forming capability. And those tests consist of, the first test would be the loss of last synchronous machine test, which we would, to test that, we basically have a project. We also have a duplicate of that project. There is reasons for that. And then we have some load in a synchronous machine. And then we essentially trip the synchronous machine and see what happens, see whether the grid forming equipment can hold the voltage and frequency stable throughout that event, essentially. The next test we have was the weak grid operation test. So this is where we would take the project and we would hook it up to just a variable strength source and just reduce the system strength to see when it becomes unstable. And for that test, we kind of, from what the testing that we've done, we've seen that grid forming equipment is able to operate typically somewhere between 1.5 and 1.1 is kind of when things start to break in terms of short circuit ratio here. Whereas with grid following, we would expect things to start falling apart substantially above that. And then the third test we had was the third requirement would be to operate in harmony with other IBRs and machines. So this would be the same setup as test one. We would have the project duplicate, some load and a synchronous machine. And rather than tripping with the machine, we would apply load step changes, fault right through in that system and make sure things are kind of operating as we would expect. And then the fourth point, this is kind of as applicable, we would have the ability to black start that would be tested as well. So we would try and energize the plant from the inverter level and then connect it to a load and connect it to the grid in the simulation and see whether it's capable of doing that. And then here's just a figure with the test systems that were used for those four tests. So I'll go through a few examples that have come out of the Hawaiian system testing. So this first one here, we had those aren't showing up super big, but the top graph is the grid forming inverter response, and the bottom graph is a synchronous machine response. In this case, we essentially the grid forming inverter didn't have a frequency droop characteristic baked into it. So when we kind of released this test, they just kind of swung against each other. So this was a fail, and this was a case where there was unclear understandings of grid forming expectations from the OEM. And I'm happy to say this is the only project that we tested that actually wasn't where the OEM actually wasn't able to prove that they had grid forming capability. So overall, we actually had a really high success rate. Another situation that ended up causing some difficulties was if you basically took the grid forming inverter and you islanded it completely with no load or anything at the POI. It turns out that that's going to be a pretty difficult situation for voltage controllers to remain stable in. So we ended up seeing oscillations in a few cases, and those are primarily mitigated by reducing voltage control gain. Another interesting one that we ran across was higher rate of change at frequency instability. So this is something that's kind of unique to grid forming. You're probably not going to see this with the grid following plant, but grid forming equipment can have inertia. So that means it's going to try and resist the changes in frequency, and depending on how that's implemented, that can be done well or maybe can be unstable. This particular trace that I'm showing here, this is a really high delta F. Actually, this came out of a frequency ride-through test. It's not like we were looking for the rock-off response or anything, but we applied like a 4 Hertz delta F with a really pretty high rock-off, and this particular project really struggled with that type of test. But I mean, it rolled through. So in the end, we ended up testing some more sensitivities around smaller delta Fs with a few different rock-offs, and the response became a lot more reasonable. So even with a really high rock-off with 1 Hertz delta F, we do see kind of that that's in the kind of the middle graph there. We see like a big drop in active power that still happens, but if the rock-off gets to a more reasonable level, like 4 Hertz per second, it's not nearly as substantial. So we decided that was probably a good enough response. Okay, here's an example of a project that was passing the loss of last synchronous machine test. It's going to be a little bit hard to tell, but the first two graphs are the grid forming project and the grid forming duplicate. The third one is the synchronous machine power. So essentially, initially we had the grid forming projects feeding the synchronous machine. The synchronous machine was acting as a motor. And then if we chip off the synchronous machine, we're kind of testing kind of a load rejection type scenario. So we see the voltage spike up to 1.1 around there for very, very briefly, and then the grid forming inverters bring that down, stabilize that voltage pretty quickly and don't trip. So that was good. And then later on, we do step in some load and we apply fault, and everything is handled pretty well. And I should say this was kind of what most of the tests look like. Overall, the projects were performing well, and they were able to handle this test pretty easily for the most part. Okay, so I'm going to touch just very briefly on an upcoming NERC guide. This is the same thing that Julia was hinting at before as well. So this is very much in draft form. It hasn't been publicly circulated, but in that white paper or guide, we do it does recommend the loss of last synchronous machine as kind of a minimum test to determine GFM in the perspective of batteries here. A lot of other tests were left out because there's a lot of the capability that should be expected of new grid following devices as well. And some of the test grid following equipment could actually get pretty close to what grid forming equipment was actually capable of doing. So we wanted to put it like a really easy test that could be very easy to distinguish the difference between grid following and grid forming. So the loss of last synchronous machine test does cover a lot of the grid forming functionalities. You do get to see fast voltage and frequency control. You do get to see phase jump power. You test system strength because it's operating in basically zero system strength, zero SCR. You do see seamless transition from grid connected to islanded, obviously, and you do see a real and reactive power sharing between devices. And you also do get a feel of the kind of effective inertia of the response. So a little bit more about the test. Essentially, it recommends 3 different initial dispatch conditions for the grid forming project. One of them where the grid forming project is operating at its power limit before the test. So that kind of tests what happens when the project briefly hits current limits to make sure it's kind of at least still stable. That test, there's still headroom in it. So it's not like we're pushing the overall system to an unstable or to a state where it doesn't have capability, but it is a nice test for confirming that operating at limits. And here's an example of that test. Similar to the last one. In this case, we had a load and grid forming project and a grid forming the duplicate of that project. And we can see that when we trip the load right there or when we trip the machine right at 5 seconds there, the grid forming inverters, they pick up that power right away. So it's essentially instantaneous. So that's that initial spike or the initial pickup is the phase angle power response. And then we get the voltage and frequency kind of leveling out over 15 seconds after that. So it's interesting to note the frequency here takes about 15 seconds to settle. So this particular inverter was really trying to resist resist how fast that internal frequency can change. But we, another OEM would have, I could show you another graph from another OEM where that frequency settles within half a second or something. And, those would both be passing the test. Those would both be classified as grid forming. So we're not distinguishing between those 2 types of responses for the purposes of this test. Okay, so just a few key takeaways from the presentation here. So basic grid forming controls in battery projects have huge potential for grid reliability. Specification of basic or minimum grid forming can be straightforward using a test-based approach, and it can be done so that it's agnostic to the control topology that's being used. And then the last point here, I think I just want to propose that we've seen grid forming capability being demonstrated in a lot of projects around the world, in actual operation and in a lot of pilot projects, and then studies, of course, are showing that the performance is really good, and it looks like we can trust these, the performance to actually match the models as far as we can tell so far. So I think there's definitely growing confidence in grid forming equipment, and it might be time to get past the chicken and egg scenario and just start requiring grid forming capability, even if we're not using it. it might be time that we have enough confidence that we can start requiring that at a larger scale. Okay, that's the end.
Okay, thank you. Okay, so we're going to go ahead and switch to our next speaker, which is Deepak Ramasubramanian. Deepak is a technical leader at EPRI in the Grid Operation and Planning Group. He leads EPRI's research projects on modeling and analysis of the bulk power system with high percentages of inverter-based resources on transmission and distribution networks areas. Okay, so I'm going to turn it over to Deepak. He's going to talk about the UNIFI Consortium and grid forming specifications.
Yeah, thanks, Ben. Before we go forward, who all know what's grid following? Show of hands. Okay, so the first wind farm connected in 1980. So that's 42 years back. A wind farm might have connected yesterday. So that's 1 day ago. Would both of them be the same type of grid following? Or are they going to be 42 years of improvement in grid following technology that causes a difference in their performance between what was in 1980 and what is today? So look, we do know from manufacturers that there has been an improvement in their performance. There has been an improvement in capability. But we have gotten so used to using the word grid following to capture 42 years worth of technology improvement to provide just one set of functionality. So what we're going to do here from a grid forming perspective is I will try to actively not use the word grid forming during my presentation. But rather the intent is to try to show what do we want from a future inverter resource? What kind of advanced capability do we want from a future inverter resource? And really encapsulate all the capability that we want from it. Maybe some of that capability is also available in today's inverter resources, but how do we go one step forward? So with that, the UNIFI Consortium is something that we formed last year, started in Jan 2022. It's a US Department of Energy funded effort, and it helps to bring together various stakeholders across a wide spectrum of industry, research, academia, and so on. And the goal is to foster this collaborative environment that we can work together to bring together or adopt this new advanced technology of inverters that we want to have. So we have 22 participants in the consortium across the various entities that we have. This is a quick picture of the consortium members itself. And what the goal we have been trying to achieve in the past 1 year is defining these specifications for a future inverter resource. Now, a lot of it aligns with what Julia, Mario, and Lukas presented. It will also align with probably what Nilesh and Nick are going to present. So it's going to be really covering this aspect where we are going towards achieving a common set of specifications across these different entities, and that's encouraging. We've seen some of this come up from different portions of the world where initially we had poor definitions of capability. There was very little consensus. We couldn't even agree on defining this advanced inverter that we wanted to have for a future power system and really trying to understand what do we want from this future inverter. But now that we have started getting some kind of agreement across the world, we've started getting collaborative efforts going on across the world, we have been able to go towards this interoperability kind of a performance specification or objective that we can use. I'll skip through this slide for the sake of time. It just talks more about what the UNIFI Consortium aims to do, and happy to talk offline. You can speak to either Aiden, Ben, or myself who are here, and we'll be happy to share more information. So the way we really took this effort forward is to really first try to understand the performance objectives that we want, try to understand the performance rules that we want these advanced inverters to follow, work towards defining terminology and definitions. We found out that oftentimes that we are talking about the same thing, but we're talking about two different terminology itself. And aligning that terminology was quite a task for us across the consortium effort. And then as we start defining these performance objectives, look towards developing use cases, look towards developing verification exercises, look towards developing tests that can not only work in a model setup, but can also work from a hardware or a field demo kind of a perspective, so that we can not only verify the models that we are getting, but also verify the actual equipment capability as it gets implemented in the field. So we have version 1 of these specifications now released. Feel free to take out your phones and take a snapshot of that QR code there. It will direct you directly to the document that we have. And these specifications, they are outlined in this manner. And although the image looks a little blurred, we'll go into it a little bit more detail in some of the subsequent slides. The aim is to try to define both for normal operating conditions and abnormal operating conditions, the behavior that we would expect from this advanced future inverter that we want to have in the system, and then go further to try to ask for additional capability. So we don't assume that every future inverter will have all the advanced capability that we are asking for, but what we want to have is a staged approach, so that depending upon what each system operator wants, depending upon what each system planner wants, they can either ask for the minimum set of capability from these advanced inverters, or they can ask for the additional set of capability with respect to the type of performance that they would want. Now, in addition to developing these performance specifications, we also had this aspect of looking at the objectives. So when we started developing these performance specifications, the goal was to map objectives of what we want this device to do and translate that to an actual specification that could be given to maybe an inverter vendor or put into an RFP or so on. And this is a kind of a mapping that we have done, wherein the objectives worked towards seamless transition, let's say from grid connected to island mode, have power sharing across the various devices as they are operating for a particular load disturbance event, look towards having some kind of a system balancing or stability kind of an improvement perspective, be able to support the loss of last synchronous machine trip, but map that out to specific aspects of the specifications document such that you can know that which section of the document is referring to which objective. So as I said, the minimum capability that we have is split up across these two sections, where you have normal operating conditions and abnormal operating conditions, or outside normal operating conditions. Now, those of you who are familiar with standards development might recognize the structure or the layout that we have, and that is intentional. Because one of the tasks that we're pursuing through the consortium is to also look at whether standards like IEEE 2800 and IEEE 1547 may need future amendments to help bring about the technical minimum capability that is required for this future inverter or this advanced inverter that we want in our system. So in aligning the specifications document in a topology or a structure that aligns with some of the standards work that we do, we think it will be easier to bring it into the standards, but we all know that standards process can be very long and there's a large variety of stakeholders involved. So we'll see where that takes us. Now, within normal operating conditions and itself, we look at autonomously supporting the grid. And that is essentially meaning that when you have the loss of last synchronous machine, it should be able to operate in a reliable manner, operate in a stable manner, within its boundary of capability, be able to support that trip, maybe bring frequency to a stable performance and so on. We also look at dispatchability. So one of the things that we saw with grid forming inverters in the initial configurations, I used the word grid forming. So one of the things that we saw for these inverters in the initial configurations was that they weren't really dispatchable. They would operate in either an isochronous manner, or they would operate in something like a master mode. So they would end up taking all the burden of the system, and you couldn't really tell it what operating point you want to get it towards. But that is something that is really important from a system planner or operator perspective, being able to have that dispatchability of these resources. So we have included that into our specification. Now, this aspect of providing positive damping to voltage and frequency oscillations is something that I'll also touch upon later on in the presentation. But essentially, it is meant to say that these advanced inverters have to bring about additional damping into the system or behave in a manner that doesn't bring about any adverse reaction into the system when they're connected. So not only help stabilize a system that may already have oscillations, but also not introduce any new oscillations that might be harmful to the system. So that is a specification that we have added into the entire document. Some of the other stuff are pretty self-explanatory, where we talk about active and reactive power sharing. We talk about robust operation in grids with low system strength. we talk about some aspects of voltage balancing and power quality. So if there is any unbalance in the system, there is a need for continuous injection of negative sequence current. We have added that into the specification so that it can help bring about balance of voltage. And then once you go outside normal operating conditions, look towards right-through behavior, look towards asymmetrical fault. So what kind of current should it inject? Is that a current that is beneficial for the protective system of today? Or is that a condition that we should work towards improving protection system behavior itself? So maybe we cannot inject sufficient current that the protection system of today requires, which might need a redesign of protection system for the future power system, but work together with the inverter and the protection system to help define that kind of future requirement for this protection system operation. We do talk about phase jumps and voltage steps, and then we talk about intentional islanding. So essentially the ability to operate in a stable manner once an island is created. So quickly touching upon some of the stuff under normal operating conditions. Essentially, we say that it should be able to respond to changes in system conditions using its local measurements. So in an autonomous manner, it should respond. It shouldn't be from the perspective of it requires some telemeter value or measurement to be provided to it in order to respond. So it shouldn't be looking at maybe a breaker status and say that, oh, okay, breaker status has opened, so I need to switch my mode of operation because the breaker status changed. Rather, it should operate based on only its local measurements without really any knowledge of what the breaker status is or anything like that of the system. So it shouldn't really need information on whether you have created an island or not created an island. It should be able to self-operate in a self-sustained manner. We spoke about dispatchability of power output, so I won't touch upon that again here. We spoke about positive damping. So this was an example that KIUC provided in one of our UNIFI seminars that we have for, this is a plug for the UNIFI seminar. For those of you who may not know, we hold this weekly seminar. It runs every Monday from 4 p.m. to 5 p.m. US Eastern Time. Please do let us know if you need to register. The link is available on our website. And we bring together a variety of folks to talk about this new advanced inverter technology that we want to have in our power system. So this was an oscillation that they had seen on their network. There's been some great work that Andy and his team at NREL have been doing with KIUC to try to look at what kind of operating behavior from these new advanced inverters may help mitigate these kind of oscillatory behavior. So is there a way this advanced inverter can inherently help damp out these oscillations? And that is something that we have included into the specifications that we want. Active and reactive power sharing. So once you have these resources operating in a system where you have a disturbance that occurs, you don't want one inverter resource to take upon the entire burden. You don't want it to behave in an isochronous or a master mode where it takes upon the responsibility of the entire disturbance. So rather, you want it to share the burden across all the other network devices in the network, and those devices may even be synchronous machines. So have the ability to really share this power and voltage, reactive power, active power burden across devices. We spoke about low system strength. We spoke about voltage balancing, so I won't talk about that in a little bit more detail here. Outside normal grid operations, we essentially say that the advanced inverter that we want to have is expected to inject current to help in the recovery of voltage. When a fault occurs, we need current to help in the recovery of voltage. This seems intuitive, this seems obvious, but we have found out that from a lot of the existing technology, that's not how they behave. So we want to really make it clear that we need these advanced inverters, these new inverters, to help provide current that will help in the recovery of voltage. We know that when the fault occurs, you cannot inject that much current to help the voltage come up, but it's more important that when the fault clears, you can help the voltage recover, because only if the voltage recovers, you can then inject active power into the network. For asymmetrical faults, we spoke about negative sequence current injection, be able to provide the kind of current that the relay needs in order to operate and clear the fault. And for abnormal frequency going outside the range, be able to help provide the kind of response that is needed. We have intentionally stayed away from certain key aspects like inertia and voltage behind transient impedance and so on, because that goes into the inverter and that looks at the characteristics of the inverter inside the black box. But rather the goal here was to try to specify these performance that we want when looked at the device from an outside as a transmission planner or operator would, so that the inverter manufacturer has the flexibility to develop and design their control as they require or as they deem fit, as long as they can meet the performance that we have specified. We have stuff related to phase jumps. We have aspects related to intentional islanding. I see that I'm running out of time, so I'll skip a little bit faster here. These additional capabilities are something that we added with the intention that not every new inverter device may be required to have this capability. So just like not every synchronous machine plant is black start capable, not every synchronous machine resource is required to be black start capable. There are only specific such plants or resources that have that capability or are required to have that capability. So the same thing can go for this advanced inverter technology, as in only certain specific plants may be required to have this kind of capability and technology. And then we talk about frequency regulating voltage harmonics. We talk about short-term rated current. So the intention of this kind of specifications is not to say that every new inverter is expected to provide 6 per unit fault current just because the synchronous machine provides it and we have gotten used to it. Rather, the aim is to either ask for that specific current if needed so that inverter manufacturers know to design the equipment for that, or work with the amount of current that can be provided by the inverter manufacturers and then look at the system impact based on that. We have been looking at black start. So it is possible to carry out black start of a system with these inverter-based resource technology, but it requires the specifications to be listed out in an appropriate manner so that you can cater to inrush current, you can cater to motor starting, you can look at transformer energization and so on with the inverters, but it has to be designed for that particular capability. And that is going to be an additional capability that may be required. As with existing inverter technology, the new inverter technology also needs to have secure communications. It needs to be able to participate in secondary frequency response. So a lot of the capability that we expect from existing inverter technology today, we do want that from this new inverter technology. It's not that that's suddenly going to go away. So we have listed that out to be very specific. We spoke about short-term rated current. We do recognize that there are constraints due to the input source. So if you have this advanced inverter, which is fed by a battery energy storage system versus it being fed by a wind turbine versus it being fed by a solar PV array, there can be differences in the behavior that you see, or there may be limitations in the capability that you can get out of this advanced inverter technology because the constraints imposed by the source behind the inverter will impact the ability of it to provide that capability to the system. So there was a question about energy buffer and so on, and whether an inverter technology in the future should mandatorily have an energy storage or headroom. So we do realize that depending upon the kind of resource you have behind the inverter, some of the capability you might get, some of the capability you might not get. But we plan the system with that kind of a constraint. And finally, we've been looking at developing test systems. So similar to what Lukas presented, we've been looking at test systems where you can test different system strength conditions. You can look at Rokoff, frequency steps, voltage steps, phase jumps. Look at also the ability of the new inverter resource to operate with an existing inverter resource. So you have IEEE 2800, you might have plants that have the capability with respect to IEEE 2800. So how does this new technology behave with that kind of a resource plant? How does it work with long transmission lines? So it's not just about the system strength in this kind of a simple setup, but with the charging of a long transmission line, with the capacitive current that the long transmission line generates, how does it behave with respect to that kind of a system topology? And can it work with the trip of synchronous machines and synchronous resources? So we have started looking at a set of tests that look at both time domain, and there we can talk offline on these results that compare the performance. And we also look at frequency domain, because we realized that supposing you look at maybe some kind of a phase jump test, if one didn't have this legend here, it is possible to not really be able to recognize the difference between existing inverter technology and new inverter technology. So we want robust phase jump right through. We want improved phase jump right through, but that's not always possible to identify only in a time domain simulation or a time domain test. So we've been looking at different kinds of frequency domain transfer functions that you can use to identify the difference between existing inverter technology and new inverter technology. And not just that, you can even use these frequency domain transfer functions to identify the applicability of a model across EMT domain and positive sequence domain. So you can verify whether the model is showcasing the exact behavior across these simulation domains using these kind of frequency domain transfer functions. So finally, moving away from the specifications, we have two aspects of the project that are looking at testing in order to verify the specifications. So we have a 1 megawatt multi-vendor experiment that will look at a variety of tests that will help evaluate whether these inverters in a small test bed can meet the specifications. We also have a plan to do a large test, which is around 20 plus megawatts, in order to test in the field for an entire plant if they're able to provide this kind of capability. So if you are looking to test grid forming capability, if you're interested, oh, I said grid forming again. If you're looking to test this kind of capability for a system, for a future inverter, for a new technology, and you have certain projects that are in your pipeline, do let us know, and we'll be happy to work with you to try to identify if they could be transformed into demo or pilot projects to help verify and test these specifications, and especially to understand the value that this new technology can provide to the system. Yeah, so we have a website, so please go to the website if there's much more information available on the website. And I think with that, yeah, that's it.
So our next speaker, Nick Harvey, who's the head of the network operability from National Grid ESO in the United Kingdom. So we'll go ahead and turn it over to you.
Okay, thank you. Yeah, my name's Nick Harvey. I work for the ESO in Great Britain. And today I'm here to talk about the ESO grid forming specification and best practice application guide. So I'm going to talk about things from in terms of the ESO journey, in terms of its development of its best practice guide. Great. Okay. Thank you. So just a very quick overview of who National Grid ESO are. We operate and balance the transmission system. We provide system access, widen access for connections and promote competition. We're the contractual interface for any new user that wants to connect to the transmission system. And we're also responsible for GB transmission charging and billing. On top of that, we work with the transmission organisations within GB, to Scottish TOs and National Grid, which we are currently part of the National Grid Group and National Grid organisation. But as of next year, the ESO will be nationalised and we will no longer be part of the National Grid Group and will be an independent ISO. So I talked about that I'm going to talk about things from the ESO perspective and the journey that we've been along. So on the left-hand side there, you can see a representation of the capacity, current capacity of generation within the GB area, and then the donut represents the sort of terawatt-hour output by the various energy types that we have. But I think what's much more interesting is the chart on the right-hand side, which I think is reflected in some of the other organisations that I've seen over the last few days. And the growth of energy requirement out to 2050, which is primarily driven by the decarbonisation of heat and transport. And the way that we're looking to meet that, or the projections of how we're looking to meet that, is through IBR resources, through onshore wind, offshore wind, solar, and interconnection. So in summary, we're going to be a network which is decarbonising, decentralising, and will become IBR dominant, and there'll be a significant decline in thermal power plants. Just to that point, next year, 2024, we'll see the closure of all coal powered fire stations within GB. So moving on from there, it was quite good to hear yesterday conversations around, you know, the physical nature of the network and the impacts of changes on the network. And one of those things that we will experience through losing synchronous plant is the reduction of national inertia, which is something that we're seeing and projected to continue to see, and also falling short circuit levels. So we're seeing all of that in terms of the reduction in synchronous plant, but then in terms of what it's being replaced with IBR resources, which is potentially, well, for to date has been grid following. There's a situation there where things could be bad and getting worse, but we also see the potential for grid forming and how that could potentially help with some of this. So in terms of the roadmap or the journey that we've been through in terms of developing our best practice guide, we sort of start off with the position of sharing insights, and we do this through 2 publications. The first is our ESO Operability Strategy Report, which reports on the sort of state of the nation in terms of electricity. So we talk about our thermal requirements, voltage, stability, black starts, systematic, adequacy, within day flexibility aspects. And we also have another publication, which is our System Operability Framework documents, which talks to different aspects, different challenges that we see on the network. And one of those that we published a few years ago was around grid forming, VSM at the time, which was in focus at that particular time. So that was the position of sharing insights. Then from there, we moved on to looking at feasibility studies. So we did a number of innovation projects which looked at VSM as a demonstrator, looking at how that compared to sort of modeled results. And then we moved on to doing testing with hybrid grid forming converters, looking at different configurations with wind farms. Then we did a demonstration with VSM and battery systems. So that took us from that sort of feasibility stage through to the technical specification and best practice place, where we had a VSM working group, and I think as has been mentioned by Lukas, we sort of pivoted away from VSM and towards grid forming. And we had GC0137, which is essentially a grid code modification within the GB area. So we formed a grid code working group, which was completed. And then alongside that, we had a grid forming best practice group, which has been developed also. So in terms of that journey, just in that very short period of time from April 2020 through to February 2022, we've had, gone from a soft report where we consulted and sought views through to developing a grid code modification, which has been employed and agreed by our regulator. So in terms of the technical specification, it provides a high-level overview of grid forming and the transmission system need. We believe the grid code modification is a world's first. It may not be, but we believe that it is. And it was, as I say, it was done in early 2022. The specification is supposed to be high level, and it's non-mandatory. So even though it is part of our grid code, it's a non-mandatory requirement, but it does set the necessary framework for specifications that can be used in future by the market, looking at the sort of potential technical specification and plant requirements, data and modelling submission, and compliance simulation tests. So it's a minimum specification, which I think has been echoed in some of the other discussions earlier, and it's not a detailed technical specification. So in terms of what it contains, in terms of the definition, grid forming plants are represented as a synchronous internal voltage source behind an impedance. Saw that in one of the other presentations as well, and also capable of contributing to some of the aspects that you can see there in terms of phase jump power, active inertia power, and damping power. In terms of compliance testing, there's a suite of tests that need to be completed, which are shown on the left-hand side, irrespective of whether it's grid forming, grid following, synchronous machines. All have to comply with the requirements on the left. So things like reactive capability, voltage control, active power, fault ride through, and the like. Then additionally, you've got the grid forming aspects, which are the additional tests which are shown within the middle box, which pertain to active rock-off power response, active phase jump power, and active damping power. And the combination of those two testing elements complete the suite of tests required for our grid code requirement. So this is where we get onto the grid forming best practice guide, which, as I mentioned, was something that we did in parallel with the grid code modification, and that was to develop out the work that had been done in the grid code modification. It's a piece of work that was co-developed with the ESO and a group of international experts. So I think that the really important thing to note with this is that we've brought together a lot of stakeholders into the space of looking at how we can improve the grid code and looking at our GB grid forming best practice guide by forming a best practice group. Through this, we developed a number of key drivers. The first of which was to provide the necessary guidance on the legal text for the grid code modification. We were looking to capture good practice within GB as well as elsewhere. And then finally, we were looking at any potential future grid code modifications that may be required as part of the future modifications to the grid code itself. So in terms of the best practice group, there were over 50 different organisations involved, from developers, OEMs, TSOs, academia, consultants, contractors. And with such a wide range of subject matter experts, we were able to use all of their contributions in 4 subgroups, looking at the definitions of GB grid forming and its functionality, looking at the analysis, tools for compliance and testing purposes, modelling requirements for GB grid forming, and compliance testing for GB grid forming. So in terms of some of the key findings that were pulled out, in terms of subgroup 1, there was some findings around using a grey box method where sort of functionality, performance, inputs and outputs of the grid forming were identified as one thing that we should be doing. There was some work in subgroup 2 around the deployment of new linear analysis tools, and that's to complement work that we would do with non-linear time domain RMS and EMT simulations. There's some work on modelling around sort of normal and abnormal conditions, which I think Deepak mentioned in his presentation as well. And then finally, compliance, talked about some more practical pass test criteria. You'll notice that some of them are detailed as sort of the level of importance and urgency. In terms of the importance side of things, that was primarily driven by OEMs and developers, because it was felt that those aspects were particularly important in terms of the performance and costs of grid forming development. So it's quite important to those parties that gets sort of developed out more quickly. So in that sense, that's something that we're working with and working on. So in terms of the final slide, this is we've through all the work that we've done to date, we see a couple of quick wins, which we're looking to implement into the second grid code modification, which we're looking to kick off earlier this year. And that will be around legal text modifications and the implementation of the grey box model. And then we're looking to develop a more detailed expert working group in Q3 of this year, where we're looking to do more focused work on the linear analysis tools for compliance testing, potentially new definitions and quantifications if applicable, and then finally the reevaluation of past criteria. So that's it.
Okay, thank you very much. So in the interest of time, if you have questions, follow up with Nick at the break, but we're going to try to squeeze one more presentation in here before break. Okay, so our next speaker is Nilesh Modi. He's the manager of the Operational Analysis and Engineering team at AEMO. If you don't know, that's the Australian market operator. Since 2012, he's been involved in various key projects and documents published by AEMO, namely the review of the South Australia system, Black Vent, system strength assessment for South Australia, and the review of underfrequency load shedding design for the South Australian system. So I'm going to turn it over to you to talk about what is happening with grid forming inverters down under.
All right, thanks. Thanks, Ben, and thank you, ESIG, for inviting AEMO to present some of our work, which we are doing down under. This work is a collective effort of a lot of people within the organization, and I'm presenting on their behalf. Oh, yeah, sure. Is that better now, Charlie? Okay. Okay, so a bit of a background on this one. Last year, we published engineering framework, which essentially provides us a pathway to achieve 100% renewable energy system and get us ready to operate a system with a lot of inverter-based resources. And one of the action items on that engineering framework was to define power system support capability for grid forming inverters to guide the OEM and developer. And as a part of that action item, AEMO did a collaboration with industry to develop this voluntary grid forming specification. Now, the word voluntary is important here. So this is still a voluntary specification. Once we have developed this one, which is going to be released in a few months' time, we will test it out with industry, and the learning of this would feed into some of the AEMO's review on the National Electricity Rule, which is a kind of a grid code. It will also feed into some of the work which TSO in Australia is doing in procuring system strength services. And it can feed into Energy Security Board's review on essential system security and pathway. So I'm going to go into the detail of this without giving a lot of background. When we started defining grid forming inverter, we asked Google, okay, what are the definitions out there? Yeah. It came up with a list of definition. What do you mean by grid forming inverter? Okay, so I have listed it. I'm not going to read it out, but what it's telling that the VDE FNN guideline, it tells that, okay, well, grid forming is maintaining constant voltage and frequency during the standard operation. If you look at NREL, it says it regulates internal terminal voltage. Look at IEEE, it kind of talks about inverter that synthesizes this voltage phasor. Looking at other definition around the world, there was a common theme that they were talking about is the voltage source converter. So that was the theme that came out. More recently, which was presented just now, coming from ENTSO-E, they also talk about the voltage source behind an internal impedance. So that was one of the articles which was presented just now. So for us, how do we define the grid forming inverter? What we say that a grid forming device maintains an internal voltage phasor short time scale following a disturbance with the magnitude and frequency set locally. And that is where it will naturally respond to any external disturbance without it relying on any measurement. And on longest time scale, of course, that voltage phasor has to change to adapt the new system condition. So that is perfectly okay. So this is the current thinking of that we have in terms of defining a grid forming inverter. We divided this capability when we try to quantify, okay, what we need from this grid forming inverter. We came up with this two set. One is the core capability, and the next one is the additional capability, which is similar to what has been discussed before on this stage. The primary driver, talking to industry, which includes OEM developers and TSOs, the driver is the cost. If there is no material cost in getting that capability on the ground, it should be a core requirement. But if there is any additional cost, which would need additional hardware or a lot of things on the ground, then it should go into the additional requirement. I'm going to step through some of this requirement relatively quickly. So in terms of core, what we are asking, we are requesting through this voluntary specification that you should behave like a voltage source. Again, you should survive the loss of the last synchronous connection, which Lukas was mentioning. That is one of our requirement through this work, that if you lose the last synchronous connection from the grid, you should stay online if you are within your capability range. Okay, so there is always a respect of the operating envelope of this inverter. So if the system condition is such a way that, okay, well, frequency is really going above very high value, I can't really stay online, it's perfectly okay. Right? But if it is a condition where you can stay online, please stay online. So you need to survive the loss of the last synchronous connection. The another one is the weak grid operation and system cell. That's one of the hot topic, at least in Australia. Westmere is a classical example. People might have followed that. So the requirement or the capability is that you should operate in a weak grid environment. Not only you should operate, but you should also support the operation of nearby grid following plant. The next capability that is table is inertial response. So it's provide the inertial response following a disturbance. And the last one is the oscillation damping. We are seeing a lot of voltage oscillation in our grid. So the requirement or the capability is that you should positively contribute to the oscillation. And there are three in the additional category, which related to the cost, because high overload capacity for a longer duration would invariably be costly. A system restart capability where you need to reserve energy just for the sake of restarting the system. That is also additional capability. And the high disturbance withstand capability. So quickly, I'll go through some of the core capability. The voltage source behavior is the internal voltage source that is a constant within a short time frame following a disturbance. And active power output of this GFM inverter is determined by this voltage phasor. At thermal limit, so if by virtue of responding to a disturbance, if it is reaching its limit, it's okay to operate in a grid following mode or some kind of a mode which is not really a grid forming mode. But that is only when you are reached at the limit. Within the limit, we expect that it should have a grid voltage source behavior. And what is expected? Okay, this is not really required behavior. This is what we expect it to be. This is some kind of a testing which Lukas was briefly mentioning. That this is the figure coming from NREL. That we expect that a small signal impedance scan of your device would look like this. When we compare the red is a grid forming and the blue is grid following. Doesn't necessarily have to be like this, but it shows that the voltage source behavior at the fundamental frequency. Again, this is just an example, I'm emphasizing it. Surviving the loss of SAS synchronous machine. This is already discussed a few times before, so I'm not going to go into the detail of it. Basically, we are asking that you should stay online. And under the island condition, you should have a capability to share active and reactive power with other online generators or online plants. And what is expected behavior will look like is something like this, where we have tested, again, in a desktop environment, a grid following plant versus a grid forming plant when we lose the last synchronous machine. Again, it's a megawatt disturbance is very, very, very small, just to make sure that we are not really, we are only focusing on the grid forming behavior, not a frequency control behavior, at least for this example. And you can see the black line is the grid following plant, where you can see as soon as we lose the grid, it sort of goes unstable and finally it just goes into a territory where it will trip. While the grid forming plant stays online and remains online. So this is the expected behavior, which this is a kind of a test as well, which Lukas was mentioning. We can test the capability using this test. This is very key for us, at least in Australia, weak grid operation and systems and support. What we are asking that you need to operate under a very low short circuit ratio under normal operating condition and when you are exposed to a system disturbance. This is recognizing its contribution to low system strength. Not only that, you should also provide the support to nearby GFL plant, the grid following plant, and enhance the overall operation of the grid. To give you a bit of an example, again, I use the expected behavior here. So one on the left is where you can see that following the disturbance, you see a blue trace where there's a lot of voltage oscillation. We are seeing it without a grid forming inverter. But when we have a grid forming inverter, the magnitude of oscillation is less. So again, we are not going to quantify it more or less, but what it is showing that it is providing a positive contribution to oscillations. One on the right hand side, there are a lot of graphs here. I'm pretty sure you can't figure it out, but I'll give you a summary of it. When you suddenly the grid strength of the network is reduced, you can see the red is a baseline where you can see a sustained oscillation. What we did is that, okay, well, let's try and test the grid following inverter. Can that inverter still able to support this voltage oscillation? And you can see those two inverters, which are grid following inverters, and one without a fast QE control, one with a fast QE control. They still wouldn't be able to manage this condition. So they started oscillating and one tripped earlier and the second tripped a little bit later when the magnitude of oscillation grows. On the other hand, when we tested with the 3 grid forming inverters, all 3 managed to keep the system stable and the voltage oscillation has disappeared. You can't see it here, but when we publish this graph, we'll make sure that you have a high resolution figure available to have a look at it. So basically, it is showing that not only the grid forming inverter can sustain a step change in the grid strength, but under that condition, it can also support nearby IBR. So that's a key thing for us, at least in Australia. The next capability which we are requesting is the inertial response or inertia-like response or synthetic inertia response, or you name it, whatever you want to name it. The key thing is that as soon as you see a change in the frequency, don't wait, don't measure it, just respond naturally like you expect it from a synchronous machine. The figure on the top right is saying that the frequency goes down from about 50 to 49.2-ish. Okay, at a very high rate. And the blue trace is the response from a grid forming inverter. Sorry, I'm missing the legend here. And the orange trace is from grid following, where grid following will stay online, it will stay online, it will do nothing. Okay. We have purposefully disabled FFR here, just to see that, okay, well, there is no FFR in grid forming, there is no FFR in grid following. Just to see like-to-like comparison, right? And you can see how it naturally it is responding, it's increasing its megawatt, and then so it's come down to its set value. The key thing for this inertial response is it would be limited by its current rating, right? So there would be a point beyond above which inverter can't provide you megawatt. And that is what is illustrated in the bottom graph, that when you go towards its maximum operating point, whether it's a Pmax or Pmin, the inertial response which you are going to get would be limited. Okay, so it's kind of a example illustration that when it is operating at 0 per unit, as an example, this is purely example, it can give you 2000 megawatt second of inertia, if you like. But when it is operating at 1 per unit, then it is limited by its overload capacity. So this is we need to respect it. Okay, well, there is an overload capacity which would undercut the megawatt response. And for more inertial response, of course, you need additional energy buffer, which is additional cost. That is not what we are requesting in a core capability. Okay, come up with what you got it. If you are operating at Pmax, it's fine. You won't provide any material inertial contribution. And this is the last slide. Wrapping up a little bit early. High overload capacity. So notionally, at this stage, we are discussing to have 1.5 to 3 per unit capacity, overload capacity. And the question is, okay, what's the duration? Is it 1 second, 2 seconds, 3 seconds, or what's the duration? We need to figure it out. There is an importance to have this sequence component, like Deepak mentioned. Okay, it's needed for a protection system. Should we ask it from the inverter, or should we reconfigure our protection system, or we need to do it both? Okay, so right now we slotted that into additional capability. You're not required to provide it. You can provide it. That's good. And again, our system restart, which high overload is a complementary to system restoration process. So it's going to have a little bit of cost. So that's very, very brief of what I had to say. Happy to take a few questions. In terms of next step, we are going to work on the testing for this each capability, different type of test, which can help to prove that this capability exists in a device. But that's the next step. Thank you. Happy to take a few questions.
Okay, thank you. Okay, since we are a little over, so I'll ask if people want